Hello and welcome to 3.6, the derivatives of logarithms and logarithmic differentiation. So in this lesson we're going to derive the formula for the derivative of a logarithmic function. And we're going to do it the same way that we did found the derivatives of the inverse trig functions. We're going to use implicit differentiation on the inverse function. So remember, the inverse of the log base b of x is the exponential function b to the x. So we're going to be starting there. So we want to find y prime of this function, log base b of x. So what we're going to do is use instead its inverse function, x equals b to the y, and use implicit differentiation on this equation. And we get 1 over ln of b times b to the y. So this derivative's in terms of y. We want a derivative in terms of x. But remember what we started with, x equals b to the y. So we can replace that, and this gives us the derivative of the logarithm base b function, 1 over ln of b times x. So since the ln of e is just 1, this gives a really nice easy formula for the derivative of ln of x, the natural log, is just 1 over x. So for example, let's look at finding the derivative of this function. This is a composite function. 2x plus 1 is my inside function. The ln is my outside function. So the derivative of the outside function is 1 over u. The derivative of the inside function is just 2. So I get 2 over 2 to the x plus 1. So notice that when I found the derivative using the chain rule, the derivative of the outside function is 1 over u, and u is whatever that inside function is. And then my numerator is just the derivative of the inside function. And that's going to be the case in general. So when you have the natural log involved in a composite function and it's the outside function, the result ends up being the derivative of the inside function divided by the inside function itself. So like in our example, the derivative of 2x plus 1 is 2, and then the function itself is just the denominator. So let's look at this example. I have the function ln of 1 over x. So my inside function g of x is 1 over x, and my outside function is the ln of u. So let's look at the derivative of the inside function. So it's the power function of x to the minus first. I find the derivative is minus x to the minus second. So that's the derivative of the inside, times the derivative of the outside, evaluated at the inside function. And the derivative of the outside is 1 over u. So I am evaluating 1 over u at 1 over x. So I actually have 1 over x in the denominator. And you see how that works out as g prime of x over g of x, and simplifying I get simply minus 1 over x. Now let's look at this example. Log base 10 of 1 plus cosine x. The log is my outside function, but remember the derivative of the logarithm, if it's not base e, needs to include that ln of b factor in the denominator. So we're going to see that it's not just g prime of x over g of x like it was for a natural log, but we need to remember this factor ln of b in the denominator when we have another base log. So looking at this, I have log base 10, and my inside function is 1 plus cosine x. So I'm going to use g prime of x in the numerator, which is going to be the derivative of this inside function, which is minus sine x, divided by ln of 10 times the inside function itself, which is 1 plus cosine x. make sure you realize that these formulas are only for when the logarithm is the outside function and the inside function is something else. There are going to be problems where the logarithm's involved in a function, but it's not the outside function. So, for example, ln of x squared times the sine of x. Here we'd use the product rule. The derivative of this first factor is 2 ln of x. That's the derivative of the outside, times the derivative of the inside is 1 over x. So that's the derivative of the first factor times the second factor, plus the first factor times the derivative of the second factor. And here's my result. Now here's an example that they have in the book that I did want to point out because we're going to need to use this in the future. So it's just something we're going to have to keep in mind. So we're going to find the derivative of the ln of the absolute value of x. And remember, we need to remember the piecewise definition of absolute value of x. This is the piecewise definition for ln of the absolute value of x. So we want to differentiate each piece. So the derivative of ln of x when x is greater than 0 is simply 1 over x. And the derivative of ln of minus x when x is less than 0 is 1 over minus x, which is the derivative of the outside, times minus 1, which is the derivative of the inside function. Here's another example where it's handy to know those properties of logarithms and laws of logarithms that you would have learned back in pre-calculus. So I have this natural log, this function, the natural log of this quotient. And instead of using the quotient rule with the chain rule, I'm going to remember that quotient law of logarithms, which says the log of the quotient is equal to the difference between the logs of the numerator and denominator. So you can see here I turned this 1 log expression into the difference of 2 logs. I'm going to find the derivative of each of these terms, this expression.